Okay, in this video we're going to look at question 4 on the January 2010 paper, which is all about standing or stationary waves. Now, this question tells us that in this figure here, we have the side view of a string on a guitar, and it can't move at either of these ends. These are fixed ends. So straight away, I know that at both of those ends, I'm going to have a node, a point of no displacement. So I'm going to jot that in now before I do anything else. And then I'm told that when it's vibrating in its fundamental mode, so the lowest possible frequency at which you can get an integer number of half waves on that string, it has a frequency of 108 Hertz. Now that has been given to us because we're almost certainly going to have to use it later, so I'm going to underline that, ready to use later on. Now the first question is asking you to sketch the stationary wave produced when it's vibrating in its fundamental mode. And on the fundamental mode, I know that I'm going to get a half wavelength on that string. Or in other words, I'm going to have one single antinode occurring somewhere in the middle of my string here. And so my fundamental standing wave on this string is going to look something like this. Up to an antinode, and then back down to the node. And I'm going to label that as an antinode. The question's not asking us to, but it's nice to know that it's there. And the mark scheme asks you to be quite specific about where the antinode occurs. It's always worth physically measuring with a ruler to the halfway point to get the positioning of your antinode. Now, the second part of part A is asking us to calculate the wavelength of this fundamental mode. Well, I know that with my length of 0.64 meters, I'm getting half a wave on. I've got my node, I've got going up to my crest and back down, but I'm not going down to my trough. So I've got half a wavelength there. So I know that that length across here, which is the length of my string, ooh, bit of a wobbly line, is going to be half a wavelength. So, to get my wavelength, all I need to do is double the length, which is 2 times 0.64, which gives me a wavelength of 1.28 meters. So that's all that you have to do for that part of the question. Remember that in the fundamental mode, you only get half a wavelength on your string. And so to get the full wavelength, we need to double the length of the string to give us our 1.28 meters. Now the next part of the question is asking us to calculate the speed of a progressive wave on this string. And as is so often the case with these questions, we're going to be harking back to our old friend, the wave equation, which is of course that the speed or the velocity of a wave in a medium is equal to its frequency times its wavelength. Now we calculated in the last part that the wavelength is 1.28 meters, and we were told at the beginning that the frequency in the fundamental mode, F0, is equal to 108 Hertz. So, plugging those into our equation, we get that our V is equal to 1.28 times 108, which gives us an answer of 138 meters per second. Rounded down. Now part B is talking about tuning the guitar. And it's saying that while the guitar is being tuned, the guitarist manages to produce an overtone, and that this overtone has a node that's 0.16 meters from the bridge. So, while adjusting the tension in the string effectively, the guitarist has managed to produce a standing wave, and we know that one of the nodes is occurring at this point here. So straight away I can draw that in as a node. I know that this here is going to be the node, and I know that this end here is going to be a node. I also know that I'm going to get a half wavelength between those two nodes. Now, the question wants us to sketch the stationary wave produced and label all the nodes that are present. Well, it turns out, if we look here, the total length of the string is 0.64 meters, and the length between these two nodes is 0.16. That's actually a quarter of the length of the string. So that means when I get to the halfway point, I can expect there to be another node here, and halfway between the halfway point and the end, I can expect another node here. So, if I'm sketching on my standing wave, I have a half wavelength there, a half wavelength there, forming a full wave, a half wavelength there, and a half wavelength there. I've got 5 nodes, my points of node displacement, and I've got 4 antinodes, which instantly tells me that I'm at the 4th possible frequency that you can get on this string, or the 3rd overtone. Now, part 2 wants the frequency of that overtone. And if we remember beforehand, when we had our basic wave in its fundamental form, we had on this same length a single wave going from the start up and down again. And that was my one wave, or rather half wave, that I could fit on that length of string. Now I have 4 half wavelengths that I've been able to fit on. I've managed to get 4 times as much wave onto that string, and so I know in order to get 4 times as many waves in, or effectively a quarter of the wavelength, that means I must have increased the frequency by a factor of 4. So all I need to do to work out the frequency is to do 4 times my original frequency, which was 108 Hertz, and that gives me an answer of 432 Hertz. If I can get 4 times as many half wavelengths on, it has to be effectively going 4 times as fast, so it's got 4 times the frequency. And the last part is saying that the guitarist wants to raise the fundamental frequency of vibration of the string. And there's actually 2 different ways that you could do this. Okay, the first way, if you imagine your original situation, so you've got a string of length L, you know in its fundamental you're going to have a node at that fixed end and a node at this fixed end. And in the fundamental, I'm going to have half a wavelength on that string with an antinode right here. Now, if I want to be able to raise the frequency, I need to effectively be shortening the wavelength. And since I know that the wavelength is going to be twice the length of the string when it's in its fundamental, then I know that if I shorten the length of the string, I'm going to reduce the wavelength. And so making that L between those 2 points smaller is going to give me a shorter wavelength. Therefore, I'm going to be able to fit more onto each string. I'm going to be able to get more full waves going past a point per second, a higher frequency. So the first thing that I can do is to shorten the string. And the second thing that I can do is, remembering that V equals F lambda, if I increase the tension in my string, that means I increase the velocity of the wave through it. And since I'm keeping the wavelength the same, so the length of the string the same, okay, so lambda is constant, I am going to get an increased frequency when I get an increased speed by increasing the tension. So the other thing that you can do is to increase the tension. And that's all there is to those questions, and I hope this has been helpful.